those of you that have your confidence intervals, I want you to just tell me the left and the right so that I can draw this up here, right? We're gonna remember the horizontal lines we looked at the other day, right? The green horizontal lines we were looking at the other day to find when you did a simulation on confidence intervals and how we were looking at the number of confidence intervals that actually captured the population's proportion. So we're simulating that here with the activity that we did in class, all right? So I just want to come around and I want to ask you so that I can draw them up here and we can kind of see. So Michaela, can you tell me what your confidence interval was?
If I did it right, I think it was 2.15.
So left and right boundaries.
Oh, the upper and lower limit?
Yes.
Oh, okay, the lower limit was 0.086 and the upper limit was 0.227.
227. All right. Okay, Addison, what's your name?
The lower limit was 0.365.
Okay.
The upper limit was 0.257.
Okay. Who else had one? Noelle, did you have one? Elizabeth, you had?
The lower limit was 0.166.
0.166.
And the upper limit was 0.46. Oh,
0.46. Is that with the new numbers?
with the 23?
Uh-huh.
Yes. It's-
So it went from 0.16 to 0.46.
Yeah, that's what when I put it into StatCrunch, I have 0.131 and 0.46.
Okay. That wouldn't be, seems odd to me, but we're gonna put it in there. Is that what you're telling me? 0.136?
Okay, 4.464 for upper and for lower it's 0.1. It changed to 131 now.
Okay. All right, Michael.
Lower limit 0.07
0.07?
Yeah.
Uh-huh.
and the upper limit 0.342.
Huge. Okay.
Did you want us to round or no?
Rounding how?
The second.
To how many, are you asking?
Just round 2 spaces. Did you want us to round or no?
Yeah.
Okay, so 0.14 for lower,
Uh-huh.
and then for upper 0.30. Sorry,
Uh-huh.
because I did round on my paper, but I just rounded.
Oh, perfect. It's all, it's an ish thing right here. Erica P,
I didn't do it.
I thought you had it.
I didn't have one.
Okay, Erica S.
Pretty sure this is wrong. I got negative 0.004 and 0.004.
That doesn't sound right.
Yeah, that's what I'm thinking.
Okay. Daniela,
I got an upper limit of 0.2534,
25, uh-huh.
and then lower limit of 1.006.
A lower limit of what?
A lower limit of 0.100.
So 10, 0.10?
0.10.
Okay. Jonathan, you have yours?
Yeah. Lower is 0.13
Uh-huh.
and upper is 0.31.
Anybody else have one that I didn't get to yet? Well, what do we see here? How many did we end up having? 1, 2, 3, 4, 5, 6, 7, right? So we don't have a very large simulation here, but what did out of all 7 of them that were reported, and I would assume yours too, Erica, What do we see happening here? Did your sample of M&Ms, did your box of M&Ms, which is a sample, right, that we are pulling from the greater population of the orange M&Ms that were produced by Mars, did your sample contain what Mars claims the true population's proportion of oranges is supposed to be? Every one of them did, didn't they? Every one of those has a red line, right, has a confidence interval that captured the true proportion, didn't it? Okay, if it was what were y'all supposed to do, a 95% confidence interval here?
Yes.
All right, so out of 100 boxes of M&Ms, if I could ever get that close, right? I never have 100 students. If I had 100 boxes of M&Ms, how many of them would we expect to capture or contain the true proportion of orange M&Ms that Mars claims? Out of 100 boxes of M&Ms, how many of those boxes of M&Ms would capture Mars's claim that the true proportion is 20%? On a 95% confidence interval, right? On a 95% confidence interval, if I have 100 boxes of M&Ms, how many boxes will capture the true proportion? 95, right? Did you think I was tricking you on that one?
Yes.
No, I'm not. Just trying to reemphasize. 95 out of 100 boxes should contain a confidence interval that has 20% in it, right? You can see in here that the confidence intervals change based on your proportion. What do we call that proportion again? Confidence interval is the interval, right? What's in the middle? What name are we giving it now? Point estimate, right? The point estimate is what we consider the proportion of your sample, right? The point estimate, think about that. This is the point we're basing the whole thing off of, right? This is the point on your interval that's the midpoint. Your margin of error is left and right on that, right? Which is why, Elizabeth, your margin of error seems really big because you're confident or because your interval was really large. So it just seems odd to me. I'm not saying it's wrong. It just seems unusual. So when we are looking at this, right, we are understanding that we can take a sampling and estimate what we really think the true proportion of oranges in a box of M&Ms would be, all right? That's what confidence intervals give us, this range of numbers for us to be able to estimate what we think the true population proportion would be. Because we can see in here, everybody's point estimate was different, wasn't it? Michael, what was your point estimate?
206.
All right, so 0.2, we call it 0.21. Alexia, what was yours? What was your point estimate?
I didn't calculate that. Oh, wait, would it be the proportion of orange M&Ms? Is that it? Oh, 0.21, sorry.
0.21 also, all right. Erica Smith, what was yours?
0.317.
Ooh, 30%, right? 31%. Michaela, what was yours? Michaela Young, 15.6%. Okay. Addison, what was yours? 16.7%. So 16, 15, right? Elizabeth, what was yours?
23.
23, 21, 21, 31. Daniela, what was yours?
17.7.
17. Jonathan, what was yours?
16.1.
16.1. So see, they're all different. They all kind of are around though, the 20% that Mars claims. I don't know if that's truly the proportion anymore. This is a fairly common statistical experiment to be done to illustrate confidence intervals. And for whatever reason, Mars stopped publishing their proportions. I don't really know why, but it was pretty cool. I thought that they did it. All right, do you get a little bit better of a sense then, and you can keep your papers now, but do you get a little bit better sense then on what a confidence interval is? Do you kind of understand what it is? It has to do with a sample. We're all gonna get different samples, right? Every time we sample, we get different values. And a confidence interval is taking into account the wiggle room for different sampling within a tolerance, right? Within a specified tolerance range. That's all the confidence interval gives us. Okay, chapter 9 is about estimating this range of values for what we think the true population would in essence be. So we move then today into our estimation of a population mean. So yesterday or Monday's lesson was about a proportion. Today's lesson is about a mean. So the same concepts apply from our proportion lesson as to this mean lesson. We still want to understand that we're going to take a sample and we're going to have an average in our sample, just like you all took a proportion and you had a proportion of orange M&Ms that were there in your box, right? So in our sampling, the average or the proportion we're interested in, right, of our sampling is going to be the point estimate, just like it was before. We are going to construct a confidence interval around the sample mean. And then pretty much basically do the same thing that we were doing last time, okay? This falls in line with most of the things that we're talking about here are repetitive from our proportion lesson as far as understanding what a confidence interval is, but it also re-emphasizes the information that we had to understand about chapter 7 when we were talking about normalcy and understanding normalcy and checking for normalcy. So again, just remember that our point estimate is going to come from the sample mean, just like our point estimate on a proportion came from the sample proportion. Before we get too far into this, however, we have to talk about this new concept. It's called a t-distribution. So up until now, we've been using z-scores, right? We've been talking about z-distributions. Okay, and what we're going to talk about today is a t-distribution. And if you you'll see today when we pull up our tests that you have the option of choosing a z or a t test. We are talking about a t-test today. So when we think about distributions, and we're talking about sampling distributions, right? We have this, this idea of degrees of freedom. The degrees of freedom that we've defined is going to be one less than the sample. There's a great explanation, I think it's on YouTube, as to what the degrees of freedom, they were able to say it really well. It has to do with the reason there's freedom there in the choice, in the sampling has to do with the last person that's drawn or something. I can never verbalize it really well, but it's a great description. But the degrees of freedom that we're looking in here has to do with one less than the sample size that we're interested in. And what we want to discuss here, what we want to identify here is, let's look at these two distributions that you see. The one on the left is a histogram for z values, and the one on the right is a density histogram for t values, or a t distribution. Look up there at the formula for z. What does that look like? What does that calculate? You've seen this before, it's just a little different. That formula up there says we're going to take the mean of the sample minus the mean of the population divided by the standard deviation of the population over the square root of n. In other words, that's how you calculate the z-score for a population, right? That's how we were calculating the z-score on a population. Z-scores are always calculated that way. You take the variable, subtract the mean, divide it by the standard deviation. That's chapter, whatever it was, chapter 3, I believe. You take the variable X, the data point, subtract the mean, and divide it by the standard deviation. And in essence, that's what we're doing here, okay? We have our variable that's changing at X bar, which would be our sample mean. We're subtracting the mean of the population and dividing it by the standard deviation of our sampling means, is what we learned in chapter 7. That gives us a t-score or a t-distribution. Look at the next problem, the next distribution, what we call a t. What is the only difference between those two formulas?
Standard deviation.
The standard deviation of what? There's an S versus a sigma, right? The S versus the sigma. What does sigma stand for? Standard deviation of what? Sigma is the curly O. Sigma is the standard deviation of the population. Little s is the standard deviation of the sample. Okay? So this Z histogram over here, this density histogram over here is really referring more to population information. Z generally goes with population information. This formula over here, this density histogram over here on the right, is referring mainly to a distribution based on samples, right? Based on samples. All right, so we are looking at, and then what do you notice if you were comparing the two histograms to each other? What do you notice? They're both normal distribution, that's right, good. What else do you notice?
There's more data in the Z-score.
Why would that be? Okay, I've never heard that, but that's a great observation. Why do you suppose that would be? If the Z, why do you suppose that would be?
It's based off of the population.
That's what I would think too, right? Okay, that's a great observation. What else do you notice? About their shapes. What do you notice about their differences in their shapes or whatever?
The sample is more spread out, like there's more data at the 10 and the negative 10 and the one for the Z-score.
Very good. So there's more data out in the tails, right? There's more data out in the tails. Think about that for a minute. When we're sampling, we have variability, don't we? Right? We have a lot of variability in essence when we are sampling. And as we get more, remember when we talked yesterday or the other day about adding people to our sample size, right? If I eventually get to kind of population type numbers anyway, there's less variability in the results, right? I heard an interesting statistic this morning on the radio. They're talking about Israel COVID numbers versus American. They did a study in Israel and a study in America. And they were talking about the validity of the study from Israel because there was something like 2 million, they were looking at 2 million people in the study. I don't know how many they were looking at the United States, but I thought, wow, with 2 million people in a study, surely that's got to provide some sort of solid information with less variability, is where my mind went on that. So yes, we have a sampling distribution that is going to be more spread out. The standard deviation would be larger in essence, I would think, okay? But the comparison or the similarities, I mean to say, of the two is that they are both following a normal distribution. So if we think about this, we do have some properties of our t-distribution that we want to kind of make sure we understand. I'm not going to ask you to repeat these to me on a test, but we just kind of want to go over them. Now, if you're just looking at the graphic up here, what we have is three distributions laid on top of each other, all right? And the curve with the normal line would be something close to the population, right? That's what we would assume the population to be. And if you follow that curve down, right? So it's got the highest peak, just like we saw above. And if I follow it down, it is the one that is the closest to the center, okay? Then if we look at a t-distribution with a sample size of 15, that would be the next highest peak. And if you follow its tail down, it is just above the blue line, so it's just above the population. And then if we look at a sample size of 5, we have the shortest peak, but the fullest tail, if you want to think of it that way, which is just like what Daniela was saying, right? There was more distribution out in the tails as opposed to the population. So our distribution, properties of our distribution says, all right, we have different degrees of freedom based on our sample size. The t-distribution will follow the same idea as our z-distribution in that it's centered at 0 and it's symmetric around that 0. The area under the curve doesn't change. It's still going to be 1. That area under the curve is still going to be 1. And as t increases or decreases, the graph approaches but never equals 0. The area in the tails, we've already talked about, are a little bit bigger, greater than, because of the variability. And then as that sample size increases, the density curve gets closer to a normal density curve. Those are just some properties. Now, the reason we point these out is because we're not going to be using a z distribution when we talk about confidence intervals to the population mean. We're actually going to shift and we're going to talk about t distributions. So we kind of want to make sure that, okay, well, if I'm going to start using this t distribution, how does that apply or how does that relate to our z distribution? And this is their relationship in essence here. Okay, so let's kind of become familiar with our t distributions here. Here I have the graph of finding alpha in essence. So if you all look there on the horizontal axis, it says t sub alpha. That's the same thing as z sub alpha, only we've transitioned from instead of a z distribution to a t distribution. The concept of it is exactly the same. Alpha is the area to the right of our critical value. Okay? Alpha is the area to the right of t sub alpha, right? T sub alpha is the critical value then that separates the area above or below. The same concept as a z sub alpha. So I want to know, what is that t value such that the area under the distribution to the right is 0.2, assuming 10 degrees of freedom. Assuming 10 degrees of freedom. So what we're looking at here says if I have a normal distribution, which I do for a t distribution, I want to know what is this value for t that gives me an area to the right of 0.2. And the other thing we have to recognize when we start dealing with t distributions is we have to have this degrees of freedom. So we'll just copy that down as the degrees of freedom is equal to 10. So when we want to know how do we find this, we're going to go to StatCrunch. So everybody go to StatCrunch. I do believe that this is the last calculator we're going to use. So when I get to StatCrunch, we'll go to Stat, Calculators, and there is a T calculator. It's going to look exactly like our normal calculator. We have our standard view, which is the one we're looking at. We also have a between view, which we recognize from the other day when we needed it, but this is the same thing. The only thing I need to really put in here, I don't have to put a mean or a standard deviation, but I do have to put the degrees of freedom. And we were told in our problem, the degrees of freedom was 10, so I don't really have to do anything there. I want to know what the area is to the right or above. And I want that value, what that critical value would be if the area above is 0.2. So we can see, did everybody get 0.8791? 0.8791? Okay. So it's a new way for us to look at that value from the horizontal axis. And it's new because all of a sudden we're talking about t-distributions, okay? So when we are sampling, as we've said before, it's very unlikely that we're going to get information about the population's value, all the information I may need. And in essence, we're shifting now to how can I do this with more of a sample method? And that's what our t-distribution is based on. It's based on a sample. So now we want to think about our formulas. So let me just point this out here. What did we say last time that E stood for in the last class period? E was the margin of error. And when we are looking at our margin of error, all right, if I had a Z value, right, if I had a Z distribution, notice that in the numerator, I would need to know the standard deviation of the population. Well, that's not always the case. And in fact, it's probably not going to be the case for the rest of our lesson. But that's the difference, right? The margin of error, if I was constructing a confidence interval and I knew the population's standard deviation, we would use this formula over here. But we don't know most often what the population's standard deviation is. So instead, we are going to be using the margin of error formula for a t-distribution. They're exactly the same except for that Z or T critical value area. What did in the last class period, what did this Z sub alpha over 2 tell us? Where did we get that value from? You wrote 3 of them down on your paper, didn't you? What are those values right there? What is the Z sub alpha over 2? Did it change? Did we have some common ones?
Critical values.
They're the common critical values, right? They're the common critical values for a normal distribution. You wrote 3 of them down for 90, 95, and 99, okay? So all we're saying right now is, okay, I may not know that number. Now I've got a sample distribution, a t-distribution, all right? So if I wanted to know what t sub alpha over 2 is, we have a calculator that we go to and find those critical values, right? So the critical values you wrote down on your paper the other day are specific for a Z value, a Z score. We use it for proportions. You would use it again if you were running a Z test. But if you're not running either of those and you're running a T test, which is what we'll be doing, then we would need to calculate that critical value on a T distribution. Okay. So how do I go about constructing these confidence intervals? Well, just put this step down, whether we happen to need it or not. Maybe you come across it in a different statistics book or a different application. First, you would need to determine, if you're thinking about estimating a population's mean, you would need to determine which test you had to run, whether it's a Z or a T test. You run Z tests if you know the population's standard deviation. We will be running t-tests because we won't know the standard deviation of the population. If you know sigma, you run z. If you don't, you run t. So after that, once you determine which test to run, then you verify that you have a random sample. Typically that comes in the verbiage of the question. You verify the sample size if you can. And you verify that you have a normal distribution that our data comes from a normal distribution. This is from chapter 7.3 when we verified normalcy. That's what we'll be looking at here. Okay. So, and then we'll just use StatCrunch to be able to do the rest of it. So you have this problem on your paper. It says a Tootsie Pop. Oh, how many of y'all know what those suckers were? Yeah, right? And they had a little commercial, right? Saying something like how many licks to get to the center or something like that, right? All right, so a Tootsie Pop is a sucker with a candy center. Famous commercial was once asked how many licks to the center of the Tootsie Pop. And in an attempt to answer the question, Corey Hyde of Siena Heights University asked 92 volunteers to count the number of licks required before reaching the chocolate center. The mean number of licks was 356.1 and a standard deviation of 185.7. Okay, take that information that we have right there. We're given numbers in here, right? Let's see if we can use context clues, reading carefully. All right, what is 92 in that sentence? What variable would I assign 92? Okay, so let's identify that. We have a sample size of 92. All right, we have 356.1. What variable do I assign 356.1?
You,
Which one?
you,
No.
X bar.
So what it says is, they just went through and said, okay, he had 92 volunteers, and the mean number of licks was 356.1. They're referring to the mean, they're referring to the sample in that case. X bar is going to be equal to 356.1. And this standard deviation, what symbol am I going to assign it?
Yes.
Because it's the sample standard deviation, all right? So that last sentence is referring to the information from the sample that this guy did. So S is equal to 185.7. That's the only information that we're given in this scenario. So if I were to ask you which test would you use, a Z or a T, what would your answer be and why? Why?
Because of it's a sample.
Okay, so sometimes you're given S and sigma, all right? But in this case, the question or the better way to think about it is what you're not given. So because I am not given sigma, because I don't know the standard deviation of the population, I will run the t-test, all right? I will run the t-test. This is another reason also why it's important that as you go through, you assign the variables correctly to the numbers, because now I can look at it and go, okay, I don't know the population standard deviation, all right? So we're going to use a t-test because sigma is unknown. Okay, so in order to look at this, let's just go in and kind of try out how to run this test to begin with. So we have the information we need. I want a confidence interval of 95%. We want to know what the confidence interval is for we want to know a 95% confidence interval for how many licks does it take to get to the center? So we're going to come to StatCrunch. We go to stat, and here are our choices. We're not going to choose the proportion because I'm looking for a mean. And now I'm going to choose a t-stat because we've already identified why. And we only do a one sample in this class, and we will do it with summary. Notice all the information that we wrote down ahead of time is now going to be used to fill in this calculator portion. So the sample mean that we found or we were given is 356.1. The standard deviation was 185.7. And our sample size was 92. We're running a 95% confidence interval. And we have our information here. Right? Did you all come up with this as well? Do you have a lower limit of 317.6 and an upper limit of 394.56? Yeah, y'all got that too? Okay. So somebody tell me, how would you interpret this in context to the problem? How would you interpret the confidence interval in context to this problem? First of all, let me just ask you, what does that mean? What does the confidence interval mean?
95% of 60 pop substance have
It's hard, isn't it? First, answer what does the confidence interval mean? What is the 317.6? What is that? The lower number of what? The average number of licks it takes, the smallest average number of licks it's going to take to get to the center of a Tootsie Pop. Good. What's that upper number? All right, what does it mean? Max average, right? It's the max average licks that it's going to take to get to the center of a Tootsie Pop. Okay. What's his face here? John, Joe, whatever his name is, right? Corey. Corey, he had an average of 356.1, correct? Is 356.1 somewhere in between those two values? Is it just somewhere in between, or in this particular case, is it a particular place in between?
It's in the middle.
Exactly in the middle. It's exactly in the middle because the confidence interval was based around his sample mean, right? So then if I wanted to know what the margin of error was, what's the margin of it? How would I calculate the margin of error on this?
Oh, you
Upper limit.
356 from
Yes, you're all right. We would subtract, right? We would subtract the upper limit and the middle, or the upper limit and the sample mean to get a margin of error. Should they be the same
Yes.
on the left and the right? They should be the same, all right? Okay, so we know what a confidence interval means. To interpret this confidence interval, we could say that Corey Hyde is 95% confident that the mean number of licks required to get to the center of a Tootsie Pop is somewhere between 317 and 394.6 licks. So in other words, if we were to repeat this process 100 times, 95 of them would have an average 95 samples of size 92, let's say, would end up with a average in that range, wouldn't it? Not every sample is going to produce the same thing, but that's our value. Okay? So really, the interpretation is not going to be any different. The process is not technically that different. We're just using a T sampling, a T statistic to be able to come up with this confidence interval. All right. Let's look at this next question right here. Crash test results. Following data represent the repair costs for a low impact collision on a simple random sample of mini and micro vehicles. So you're given the data right there. We want to know some things. We want to be able to go through the process, right, of our sampling. We want to go through the process of our sampling to construct our confidence interval. But before we go too far, we want to determine, am I looking at a Z or a T test here? What do you suppose I'm looking at? Which one do you think I'm going to run? T test, that's right. And why would you say that? I don't have any information about the population, right? I only have information about a sample. Okay, so in StatCrunch, we're going to go put these numbers in. All right, all of us are going to put these numbers in. So just copy down the numbers you have on your paper right there. Did you all get the data entered into the StatCrunch? Okay, so we're going to go do some things on this. We are eventually going to run a test on this. Would we be running a test using summary data or raw data? Raw data, right? Because we have raw data here. I don't have any information on this, do I? I don't know what the mean is. I don't know what the standard deviation is of this sample set, anything like that. Okay. But what I do need to first decide is I need to verify that this is coming from a normal distribution, because I don't have very much information here, right? I'm not told anywhere in here that the average, the repair cost for low impact collision comes from normal distribution. So I need to verify it before I apply my normal properties. We do that by using a normal distribution. Remember when we did our normalcy, checking for normalcy in chapter 7.3, you just took a test over, right? We do that using our QQ plot. So I want to come here. I want to come here to graph. QQ plot. We're going to select crash. Is that, or whatever column you put the data in, and we're going to add our correlation statistic. Okay. So we have this information here, right? Just looking at the graph and ignoring that correlation statistic you see at the top, what would you say about the data? Does it look like it's normally distributed? It doesn't look like it to me, all right? I agree with that, but let's do a little bit more investigation on this. And in that problem right there, let's see, I'm gonna pull this over here. We knew that the correlation statistic that came up on that screen was 0.966, correct? Is that right? Okay. And we had a way to also verify whether or not something was normally distributed by comparing the correlation statistic R and the critical value, right? I was comparing the two things together, the critical value. Remember when it was the only time I told you to look at the table? Remember that? Right, the table of values. All right, so I don't have in this problem here. What was our sample size? It's a sample of 10, correct?
Yeah.
Well, I'm going to tell you, pretend that I just have the table memorized of critical values for sample sizes. And I'm going to tell you that the critical value associated with a sample size of 10 is 0.918. All right, that comes from the table of values. Okay, do you believe me? You all understand where I'm getting that number from? I have my tables memorized. That's how come that's it. All right. So if I have 0.966 for the R value and 0.918 for the critical value, we can see that R is greater than the critical value, correct? Okay. And what we learned in that section was that if that's the case, then our conclusion is that this does come from a normal distribution, even though it didn't quite look like it when we did the QQ plot. All right, so we kind of verified it using our R and C and critical value. Now, the other thing that we would look for is we can also draw our box plot. Remember how to draw a box plot. So if I come over here and I draw a box plot, and I'm going to put it horizontally, and I'm going to check for outliers. Looks like the distribution is a little skewed, but in essence, it's not going to be too bad, right? There are no major outliers, so that would be the other thing that you would be looking for. So we're going to verify using our QQ plot, R versus CV. And we're also going to verify any outliers using a box plot. Okay, so we're good to go. We can move on because the next thing it says on our paper there is to construct and interpret a 99% confidence interval. So we come over here to stat, T-stats, one sample with data this time. Choose the crash or whatever column you were using. And click and change your confidence interval. Which one are we doing? 99%? 99%. All right. So what's our point estimate for this sample?
1756.
Good, 1756.5. Remember that the point estimate is going to be the same as the sample mean. So in this sample of car repairs, the average cost is $1,756.50. And we have a confidence interval, a 99% confidence interval around the lower and the upper limits, right? So we have a lower limit of 721 and an upper limit of 2791. Okay. So the question on your paper, I believe, says, the next question says, before we do it, do you think a 95% confidence interval would be wider or narrower? If I did a 95% confidence interval for this, before we ever do it, do you think it's gonna be wider or narrower? And why?
It's narrower because,
It is. We're out. Why is it narrower? Just got you started. Why do you suppose it's narrower? I always think of it in terms of this. What?
This area. Would it be covering like more like, hold on, let me try to verbalize it.
that's my thing, I'm like,
I don't know. I can't think. This side over here is represented very well. What do we got it going over here? How many in a 99% confidence interval, right? How many of them do I have to catch? How many confidence intervals are going to catch the true population? Okay, so I'm missing one, right? Okay. In a 95% confidence interval, how many of them are going to catch the true population's mean? So I'm catching less, right? how about this? I can miss more, can't I? I can give up 5 of them. I'm all right with giving up 5 of them on a 95% confidence interval. So my interval can be smaller, can't it? I don't have to catch as many, right? So as our confidence interval increases, so does the width. As our confidence interval decreases, so does the width, right? My width is going to get smaller because I'm willing to miss more intervals, right? I'm willing to let more samples basically come back with it not capturing the true population is what would happen, right? I'm willing to give those up. All right.
So
Let's
when
check.
when it decreases, it gets thinner, and then when it increases, it gets wider.
Okay. As the interval increases, it's got to get wider because we have to capture more. We're not willing to miss hardly any. Conversely, if I go down, I can make it smaller, right? I'm willing to miss more of them, right? That's on a confidence interval. Basically, the confidence interval was behaving in the same way, the width was behaving in the same way the interval was behaving. As the confidence interval increases, the width increases. As the confidence interval decreases, the width decreases. Right? That was different from us talking about sample size.
I'm sorry, but 99%, it's gonna be narrower, right? And then 95% is gonna be wider than 99%, or is it the other way around?
It's the other way around.
Okay.
The other way around. And let's see, all right? So we have, the best way to look at this is we have an interval that is between, on the left and the right, the interval was between 721.15 2791.85. And the middle is at 1756. That's the middle. Run a 95% confidence interval for me now.
it's gonna be between 1035.8 and 2477.2.
Did the middle change? So those numbers got smaller, didn't they? right? So the width the width is smaller, isn't it? Because I can miss more of them. And it would be smaller even as you keep decreasing the size of your interval. Remember, a confidence interval, the level of confidence, I mean to say, the level of confidence that we are looking at says, I am confident that if I run a sampling, I'm confident that if I were to go out and sample, that if I did that sampling 100 different times, 95 of the times I repeated the process, I'm going to capture what we believe the true population to be. It's 5% of the time I'm going to miss it because my sampling is wrong or something happened, right? Maybe you're sampling in an area that maybe your sample is just going to miss a large part of it, right? We have to be okay with errors to occur, in other words, all right? And we're going to be all right with, if I'm sampling 100 different times, 5 times out of 100, it's not going to be right, okay? But if it's high stakes, if I'm not willing to give that up, then I'm going to make it 99% of the time I capture it. So my interval has to be larger to capture more of them. Okay. Okay. So now let's look at the last thing that we kind of want to discuss here. It has to do with, well, how do I know what size to get? Remember last time we talked about what's the magic number? What is the sample size I would need? Now on this is the formula that we would be using to calculate by hand. Remember, this is us calculating by hand how to find the sample size I would need. In StatCrunch, you're going to be using the Z-stat. Put a star by that, put an asterisk by it. Don't use a T-stat. Use a Z-stat. To calculate this, okay? Calculating it by hand, you can see here how to do that. What does lowercase s stand for again? The standard deviation of the sample. What does z sub alpha over 2 represent?
Critical value.
The critical values, that's right, the critical values. We wrote down the common critical values, but yes, those would be the critical values. What does E represent? Margin of error, that's right, okay? All right. So the question we want to answer says, a doctor wants to estimate the mean HDL cholesterol of all 20 to 29-year-old females. How many subjects are needed to estimate that HDL cholesterol within 2 points with a 99% confidence interval and a sample standard deviation of 13.7? Okay. So if I were, let's calculate this first by hand, and then we'll just go check it using the calculator. Okay. So what would the sample size need to be? We know that we have, get some stuff written down here. We know that we have a sample standard deviation of 13.7. We know that our margin of error is 2 points. Look at that closely. They didn't say percentage points, did they? Like they did the other day. The other day they said within 3 percentage points. Today we're saying 2 points. Okay, so we're not going to change this to a decimal. That's my point here. So we're using 2 because they did not say 2 percentage points. all right? That's the difference. We're using a confidence interval of 99%. So Z sub alpha over 2 at a 99% confidence interval was what? It's on your paper. That's 95%. Let's do 99.
Oh.
2.575. Okay, so we have everything we need to calculate the sample size. We're gonna take 2.575, multiply it times the standard deviation of the sample, which is 13.7, divide it by the margin of error. We're gonna do all that first, and then we're gonna square it. And we're gonna round up to the nearest integer. So do what's inside of the parentheses first, then round it up. Practice it on your calculators right now. Order of operations tell you to multiply the numerator, divide it by the denominator, and then square the whole thing. So you should get 312. Does everybody get 312? Yeah? Okay. Okay, now let's go try this using our StatCrunch. So in StatCrunch, where do I need to go? I want to know the sample, I want to know the sample width, or I want to know the sample size, excuse me. Where do I need to go? Yes, very good. So stat, Z stats, one sample width. Z stat, one sample width. Our confidence interval, we're gonna check our math on this. We just did a 99% confidence interval, I believe. The standard deviation is the sample standard deviation we were just using. What is the width I'm going to use here?
The margin of error.
Doubled. Remember in the
Oh.
calculator, I gotta double it. So in the calculator, when I'm using it on StatCrunch, I've gotta use 4. Sample size was 312. Okay. All right. What would the sample size need to be for a 95% confidence interval?
181.
Everybody able to get 181? So as I decrease the confidence interval, what happened to the sample size I needed? Decrease. Right, it decreased. Remember that when I lower the confidence interval, when I lower the sample size, I'm gonna have more variability, but I'm also dropping the confidence interval down, so I'm okay with that, right? Very good. Now, the reason we needed to come to our Z-stat to find out the sample size is because we have to multiply by the critical value, right? The critical value of our confidence interval. Okay, so I won't ask you for this, but I want to highlight something. The critical value that value or that formula right there is what the calculator is doing for us. This is giving us our critical value in essence, right? It's our T-score, okay? So just like this is our Z-score. But do you notice you have to have a sample size to be able to calculate that? So it's kind of a circular, like you can't calculate that, right? You have to use the populations. So somehow or another, they're using the population when they're calculating this in the background. We have to use a Z-score or a Z-stat to be able to calculate the sample size because we don't know the sample size yet. Okay, so let's think about these things really fast. And I'm going to put these up here on the board just so that you'll have them written down, or you'll have them available should you decide to take a picture of it. All right, these are answering, I believe, the last of the questions. I think these questions are on your paper at the end. Two things that we want to look for that tell us to construct a confidence interval on a population proportion, right? So this is kind of like, how do I know which one I'm supposed to be using when I'm talking about confidence intervals? You're given a scenario, right? If you're given sample data that is qualitative, two outcomes. Orange M&Ms or not orange M&Ms, right? That's a qualitative variable with two outcomes. Therefore, you're going to have a sample proportion with the number of successes out of the number of trials. X successes out of N trials. How many orange M&Ms did you have out of your total box of M&Ms? Okay, that's when we would use our proportion. And then when we're thinking about a proportion, the validity conditions that must be met is it's got to be obtained from a simple random sample. Again, generally that check box is kind of listed when they say it in your setup. We're checking for NP1 minus P to make sure that that is greater than or equal to 10. And then if we can, we're trying to make sure that our sample size is no more than 5% of the population. Okay, everybody took a picture of this or is feverishly writing it down? Okay. Two things that you would look for to construct a confidence interval around a mean. You're trying to look for something, some sort of data or something that's indicating that it is a quantitative variable. And then you're going to make sure that your summary information does include both your sample mean, the standard deviation of the sample, as well as the sample size. Those are the three things that you need in order to run it in StatCrunch anyway. So the validity conditions that have to be met for a sample mean is it's got to be greater than the sample size N. When I'm running this, when I'm doing a confidence interval on a mean, N has to be greater than or equal to 30. That invokes the central limit theorem. That's the best way to look at it. If you can't do that, another way, option B, would be to check using the QQ plot and that there's no outliers, right? That was why we did the box plot as well as the QQ plot. Okay. right,